Now let us analyze this problem. Show that the sequence of functions fn's just defined like this is pointwise convergent but not uniformly convergent on R. So, and also find the uniformly convergent subsequence. Let us first understand the pointwise convergency. Okay, so fix any real number, then calculate this limit, n goes to infinity, f of n x. So in the both cases, when n is even or odd, n will be increasing and x would be just constant. So this pointwise convergence for any x would be just 0. Okay, because either, limit n goes to infinity, x over n gonna be 0, or limit n infinity 1 over n is gonna be 0. Now pointwise limit is then 0 function. Now is it uniform or not? I'm gonna just use this lemma. It says that to be able to show fn's are not uniformly convergent to the pointwise convergence function, if for some epsilon, if you can find some subsequence of fn and some sequence of xn in the set such that this is always bigger than epsilon 0. So we have found that. Okay, let me just, fn's are pointwisely convergent to 0. Now consider this. Fn case are just 2. Okay, I'm gonna choose this n case as even numbers. So I'm just gonna put f2 case x. So using the definition of my sequence, it is gonna be x over 2 case. So now I'm gonna create some x case also. Let me just put x case equal to k. Okay. Now if you also plug this in, you will have f2k xk minus 0, which is my pointwise convergence point. So this is k over 2k minus 0. Okay, let me not write 0, which is 1 over 2. Okay, if at the beginning, if I choose epsilon to be, or in our case it is epsilon 0, right? So if I choose my epsilon 0 to be 1 over 4, then this is always bigger than 1 over 4, which is epsilon 0. So it means that my convergence is not uniform. Okay, so on real numbers to 0. Now I can also find some uniform convergence subsequence. Now consider the subsequence f2k plus 1. Okay, then it is by definition 1 over n, which is constant in terms of x. It's just a constant number for any. Okay, it's not k by the way, it is k plus 1. Okay. So for every x, it is just a constant number. Okay, so it is like a constant graph. For okay, you are changing k's, but at each k you get a constant graph. Okay, that's why it is all, of course, uniform. And you can also calculate, as to be able to prove this clearly, you can just put supremum definition f2k plus 1 x minus 0 x in real numbers. It is just supremum of 1 over 2k plus 1 when x is in real numbers. But as you can see, it is independent of this x because it is just a constant number, as I was trying to tell you in this case when I was talking about constant graphs. If you are gonna take this limit when k goes to infinity, it approaches to 0. So by the definition of uniform convergency, f of 2k plus 1s are uniformly convergent to 0 as desired. Now study the uniform convergence on 0, 1 closed of the sequence of this kind of functions. So first, pointwise. So if x is 0, then limit n goes to infinity f of nx, or just let me write it explicitly, 1 over 1 plus 1, right, minus 1 square 1 is 1 over 2. If x is not 0, I mean if x is in this interval, then limit n goes to infinity 1 over 1 plus nx minus 1 square. Okay, this x is not fixed number, and by Archimedean principle, nx, since n is increasing, would exceed any number. It can also be negative, right? No, because x is positive, n is yeah, even if it is negative, this will be very big number because you are then taking square. That's why this is gonna be 1 over some very big number, okay? Or you can just apply the correct limit ideas to find this is 0. So at the end, fn's pointwise converging to f of x defined by 0 if x is not 0, 1 over 2 if x is 0. But as you can see, this is not continuous function, not continuous function. But each fn are continuous function, right? For example, n is 1, 2, 3, 4, 5, etc. You don't have any thing make this singular because it is just a rational number, quotient of 2 polynomial, right? For any fixed n, this is never undefined. This is defined on this interval, so every time it is continuous. So if it was uniformly converging to f, the limit would be also continuous, but in this case it is not so uniform, not uniform convergent, not uniformly convergent on 0, 1 to f of x. This is f of x. Now let us also find the pointwise limit, pointwise. If x is 0, then f of n x is 0, right? So because I'm talking about x equals 0, because it makes this n is disappearing, make this disappear, right? That's why I'm talking about 0. If x is not 0, then let us calculate this limit n goes to infinity, f of n x, limit n goes to infinity, x square over x square plus nx minus 1 square. Now x is just a fixed number in 0, 1, but it is not 0. So with a similar idea in the part A, this is gonna be for fixed x, I am increasing the n, so this will be 0. Or you can, no, you don't need to. But, okay, let me do it, okay. X square plus n square x square minus 2nx plus 1 square, which is 1. So above we have just x square, but I'm taking limit in terms of n, so they are just constants, so n square is increasing, so this is becoming infinity, so this limit is 0. So pointwisely f n's are approaching to f of x, which is just 0. Now I cannot use the similar idea in part A because everything was continuous and my 0 is also continuous, so I cannot conclude this is not uniform yet. But let us apply the supremum idea. Supremum f of nx minus f of x, which is 0, when x in 0, 1, I can rewrite this as sup x square over x square plus and x minus 1 square x in 0 1. I can take this absolute value or not, because everything is positive, so no problem. Now I can make this critical points analysis, etc. But but this definition shows me that I can use some subsequence in x. Okay, for example, if you put x equals to 1 over n, so this is gonna be 1, so 1 minus 1 0, this is gone, so I'm putting x equals to minus 1 over n, so this is 1 over n square, 1 over n square, this is 0, so I will get 1. But this 1 cannot reach the 0, it is just constant, so it proves that it is not uniform. Now consider f of n 1 over n minus f of x. So I am finishing my supremum idea because it didn't work. I don't want to deal with this kind of critical points, etc. Let me just use this subsequence idea. So this is just 1 over n square over 1 over n square plus 1 over n minus 1 square. This is 0, so this is just 1 and cannot approach to 0, so fn's are not uniformly converging to 0 on 0 1. Now again the same question. Let us first find the pointwise limit. Fix x in 0 1, so limit n goes to infinity. By the way, if x is 0, then this is 0, this is 1, so this is 0. When x is 1, this is 0, this is 1, so it is 0. So maybe we can choose x is not 0 and 1, but inside of the 0 1. Maybe it does not even matter. 1 minus x. So this part is just a fixed number, right? Because x is fixed and bounded thing. So it is fixed. When x is between 0 and 1, n is increasing. So this is gonna be 0 as n goes to infinity. So pointwise limit is always 0. So pointwisely fn's are approaching to 0 pointwisely. Okay, for all x in 0 1. So it seems nice because we couldn't find this is discontinuous, so that we cannot conclude that the convergence is not uniform. So let us try to apply supremum idea, right? Supremum f and x minus 0 supremum x 0 and 1 minus x so 1. So let us now we can apply this critical points, etc. Take the derivative of f and x with respect to x, of course. I mean f and x dx. So it will give me an x n minus 1, 1 minus x to the power n. Taking the common parentheses of x n minus 1, we have n minus x n minus x. So let me maybe simplify it. No, it's enough. Okay, so to be able to find the critical points, we don't have any undefined points here, but I can just equate the 0 so that I can find zeros. We have no singular points. So here x can be 0, so x can be 0, or x can be this thing means minus 1 plus n multiplied by x, so x is n over n plus 1. So we have two critical points. If you make the table, so 0 and n over n plus 1 for any x, for any n, okay? For any n, you are fixing n, and you are calculating these critical points for this fixed fn x, okay? So it means that for each n, you have two critical points, 0 and this thing. 0 is probably not a maximum, right? Because I'm talking about supremum, so I need some maximum or local max things. So 0 is not maximum because it is just 0. But here I can get something. So yeah, since 0 is not maximum, I don't have to do anything at all, right? This is probably local max. So when you put this supremum probably, okay, first let me analyze, then we can put. So in this case, this means n plus 1 to the power n, 1 minus n over n plus 1. Let me simplify. As you can see, this is obviously not 0. So it is bigger than 0. So it is actually a local maxima, right? So this is local maxima for this supremum. So it is indeed equal to supremum of x and 1 minus x in 0, 1. So now we can take the limit. If this limit, when n goes to infinity, is 0, then my convergence is uniform. So let me calculate this limit. N goes to infinity, n plus 1, and 1 minus n over n plus 1. So let me simplify. Mm, 1 over n plus 1. So this left limit, this thing, this part I mean, is gonna be limit n goes to infinity, n plus 1 minus 1, so 1 minus 1 over n plus 1 to the power n. So if you remember from the calculus courses, this is e to the power minus 1. So this is gonna be just 0, so 0, 1 over e is 0. So as you can see, f of n's are uniformly converging to 0 on 0, 1. So actually the same question, if you remember, part C was f of n x to the power n 1 minus x. So we have calculated in this part C that my local maxima at x equals to n over n plus 1. So as you can see, when you take the derivative of this function, n is independent of x, so you will find the same local maxima. But first, let me calculate the pointwise limit. So if x is 0 or 1, then f of n x is just 0. So if x is between 0 and 1, then limit n goes to infinity, n x to the power n 1 over 1 minus x. So since this 1 minus x is independent of this limit, 1 minus x, limit n goes to infinity, so n x to the power n. So since this x is less than 1, of course bigger than 0, this is gonna be 0, but this is gonna be infinity. That's the problematic part in this part. So we would have infinity multiply 0. To be able to solve it, we can apply L'Hopital, but first in the correct formula. So limit n goes to infinity and x to the power n is limit n goes to infinity n over x to the power minus n. Now you can apply, because above is gonna be infinity, below is gonna be infinity, so apply L'Hopital. Of course we are applying L'Hopital when we change this n to another variable in the real valued functions. Otherwise we cannot apply L'Hopital, but we are main show is mathematical analysis, not calculus. That's why they are just little details. Here, if you apply L'Hopital, lim n goes to infinity. What is the formal derivative of n with respect to n? 1. What is the derivative of x to the power minus n with respect to n, which is minus x to the power n multiply ln x. Now, if you take the derivative, okay, first let me just write in this form x to the power, by the way, there should be some minus x, n over ln x. Ln x is just a constant, so when you take the derivative, this part is gonna approach to 0, so 0 multiplied by constants is gonna just be 0. So this thing is indeed 0 everywhere. So pointwise limit fn is pointwise approaching to 0. Now I was talking about this local maxima, etc. So the local maxima for each n is just n over n plus 1. It is not changed. So let me apply using the supremum formula. So supremum of f of n x minus 0, which is our pointwise limit when x in 0, 1. So this is supremum. Okay, what was fn? And x and but since my local maxima is this one, this supremum would be less than or equal to f of n when n over n plus 1, which is n multiply n over n plus 1 to the power n multiply 1 minus n over n plus 1. If you simplify this, and let me just make some space, gonna be, okay, n to the power n plus 1 over n plus 1 to the power n multiply 1 over n plus 1. So it is indeed n plus 1 over n plus 1. So if you take the limit, okay, if you take the limit n, by the way, since supremum is bigger or equal to, so this should be bigger than equal to. Okay, now limit n to the power n plus 1 over n plus 1 to the power n plus 1 and goes to infinity. Just let me rewrite it. N plus 1 minus 1 minus 1 over n plus 1 to the power n plus 1. As you calculate this, maybe you can change the variable n plus 1 to n. It does not matter. You will find that this is the limit of 1 over n, 1 over e, which is not 0. So it means that the supremum never reaches 0 when you take the limit in terms of n. So it means that the convergence is not uniform. So n, x, and 1 minus x are not uniformly converging on 0, 1 to 0. Again, this is very similar to the previous questions. So first let me find the pointwise limit. As you can see, x is 0 or 1, then f of n, x is just 0, right? When you plug n 0, x is 0, 0, x is 1, this part is 0, so f is 0. If x in 0, 1, then limit n goes to infinity, n cube x to the power n 1 minus x to the power 4. Now, as you can see, this is independent of the limit because variable is n. You can take it out. You can calculate this n cube, multiply x to the power n. But again, by using L'Hopital rule, you will find that this limit is just 0. Because, okay, n is increasing, but this is less than 1, right? So this is gonna increase more in the denominator, so you will end up with 0. So this exercise maybe, because it is not the main show. Now, point-wisely fn's are approaching to 0. Okay, so let us calculate the supremum. Supremum f of nx minus 0. Okay, şurayı kötü. X is in 0, 1. To be able to calculate it, maybe we can apply critical points for any n. Take the derivative of f of n and x with respect to x. You will find that okay, n cube n x to the power n minus 1 minus x to the power 4 minus n cube x to the power n 1 minus x to the power 3, and of course we have 4 here, and minus 1 is the derivative of 1 minus x. So this is correct formula. If you just simplify it, let me try. So let me take n cube and x to the power n minus 1 and 1 minus x to the power 3. Okay. In this parenthesis, I have extra n and 1 minus x. Minus, I have minus 4 and x. Okay, that's all. Minus 4 and x. Minus 4 and x. Okay, let me simplify more. Or let me do it here. This part is n minus nx minus 4x. Or in terms of x, this is just n minus n plus 4x. Okay, so since this cannot be 0, right, because x is between 0 and 1, right, here, pardon, and of course it can be 0 at 1 and 0, but they are just trivial, right? When you put x 1 or 0, you will find 0, so it is not obviously maximum. So the interesting critical points will come from here. In this case, it is x n over n plus 4. So if you put this in, you will find a non-negative and non-zero number. So it is your local maxima. Yeah, of course I'm passing through a lot of details, but yeah, this is just brief explanation. So in this case, supremum f of n x in 0, 1 is gonna be just this function, right? F of n evaluated at this local maxima because it is supremum. So for this x, right, when x a equals to this number, so this supremum takes the biggest value, which is itself, right? So f of n over n plus 4. If you plug this number in, you will end up with n plus 1, n plus 1, n plus 1. So you can calculate it. If you take the limit, n goes to infinity. Okay, this is not correct. Okay, let me do it. Okay, let me do it manually. When you plug this number in this definition, what do you get? N cube n over n plus 4 n and 1 minus n and 4 to the power 4. So f of n plus 4 is just okay, we have we have 4 over n plus 4 here, right? To the power 4. So at the end I have 3n, nn, and nothing here because it is it is 1, right? It is not n. It is probably 1. 4, I'm sorry. Okay. So it is n to the power n plus 4, n plus 3, multiply 4 to the power 4. In the denominator we have n plus 4 to the power n plus 4. Now it is okay. Yes. Now when you take the limit, since we have another power, right, extra power, it will give me just one n, e, and the other part will be 0. So explicitly let me compute it. So f of limit of n goes to infinity, f of n over n plus 4 is just limit n goes to infinity. So n over n plus 4 n plus 3 multiply 4 to the 4 over n plus 4. So let me just calculate this limit. First part, limit n goes to infinity, n plus 4. I can just add 4 and subtract 4. That I can get the following: 1 minus 4 over n plus 4 to the power n plus 3. Since it is a bit definition of the exponential, so you will get e to the power minus 4. It's exercise, so it's very easy exercise, but it needs some details. And this part is gonna have limit 0, so this part is gonna approach 0. So overall everything is gonna approach 1 over e to the power 4 multiply 0, so 0. It means that my supremum, which is equivalent to this sequence, which has limit 0, it means my convergence is uniform. So fn's are uniformly converging on 0, 1 to 0. Now consider this sequence. Okay, let us start pointwise limit, fix n x in this interval, then take the limit n goes to infinity and x squared over 1 plus nx. Of course, if x is 0, this is 0, right? But you will find that when you take the limit, you are taking limit in terms of n. So what is the coefficients of n? X got x, so this limit will be just x. So this consists of the point x0, right? When you put 0, you get 0, in this too. So the whole information is stored in this x. So indeed, so fn's are pointwisely approaching to x. Pointwisely. Okay. Now let us find it, whether it is uniformly convergent to this function or not. So let me calculate this f of n, x minus f of x. In this case it is x, and x squared over 1 plus nx minus x. Let me simplify. We have some cancellation, right? These are gone. So you will have x over 1 plus nx. Since n and x are positive, that's why it can come out as positive. Now let us analyze the critical points. Critical points. Let me call it g of x. Take the derivative of g of x, which you get 1 plus nx minus x n over 1 plus nx. So you will have 1 over, okay, this square, 1 plus nx. It is always strictly positive, I mean increasing. So I can find then supremum of fnx minus x in 0, 1 as, okay, now I have calculated this, right, as simplifying to g of x. So I have calculated that this function, okay, this with absolute value, is always increasing because its derivative is always positive. So since we have some bounded region, since it is increasing, the supremum would be at the end of the interval, which is 1. So when you put x equals to 1 in this function, you will get the supremum. So since we have calculated it was g of x, put x equals to 1, so it is 1 over 1 plus n. And as you can see, if you take the limit as n goes to infinity, this is 0, so fn's are uniformly converging to 0, 1, on 0, 1 to x. Okay, first calculate the pointwise limit. If x is 1, then f of nx is equal to 1 over 2. If x is not 1, but inside of the 0, 1 interval, then limit n goes to infinity 1 over 1 plus xn is gonna be 1, I guess, right? Because since x is less than 1, right, strictly less than 1, when you take the limit, this would be 0 when n goes to infinity. So you will end up with 1 over 1 plus 0, which is 1. So pointwisely f and x are approaching to f of x, which is defined by like this: 1 if x in 0, 1, 1 over 2 if x is 1. So as you can see, for every n, this thing is continuous on this interval. But if it and I have calculated pointwise limit is this: if it was uniformly converging to f of x would be also continuous, but in this case it is not, contrary to our functions that are always continuous. So it is not uniformly continuous. So f of n are not uniformly continuous on 0, 1 to f of x, this f of x.